In the last section, we started talking about runtime complexity, and we took a look at our reverse algorithm, our string reverse one, and the steps algorithm. We had said that because the string reverse algorithm had to do one additional unit of work for each character that was added into the input, we would have a linear runtime because there was a one-to-one relationship between the amount of work we had to do and the input set. Then for the steps algorithm, we had said that each additional piece of input that we got, or each increment to it, I should say in this case, meant we had to do n squared more things. So we had to do significantly more work each time our input increased. Now, one thing I want to make really clear here, because some of the nomenclature that I've used is not super obvious, notice how during our steps algorithm, when we were putting it together, we had that input, or the input argument was called n. This n right here of 4 or 3 or 2, this is a different n than the n that we're using over here to specify our runtime. So over here, the input to our algorithm, this might have been better indicated as like, number of steps or something like that. We could call it steps. Maybe that would have made life a little bit more clear. So the two are related, but I'm not saying that it's the same exact number. That's all I mean to say. Okay, so let's now continue by looking at some very common runtimes that we will use to identify many different algorithms. Okay, so here's some notes on some different runtimes that we're going to see in the wild. These in general are really the runtimes that you want to keep in mind. There are other runtimes that exist. There are other types that you have to do a little bit of math to calculate, but in general, many of the different interview questions you will be asked will fit into one of these buckets or some combination of two. And we'll talk about some of the rules around when you might combine two and all that kind of good stuff. So I know that it's really boring when a presenter reads notes directly off a slide or a diagram. Nonetheless, I do want to quickly read through some of these descriptions right here because a lot of them contain some very important notes. So we're going to start at the top and talk about this first runtime and then go down towards the bottom. So let's first start talking about constant runtime. Constant runtime means that no matter what our input set is, or no matter what input we give to the algorithm, it's always going to take the exact same amount of time to execute the algorithm. So for example, if we came up with some amazing magic algorithm that does not exist, but if we came up with some amazing magic one where we said, as the length of string that we put into our string reverse function changes, it's always going to take exactly the same amount of time to reverse it. If we came up with some magic algorithm that did that, we would refer to that as constant time. However, such an algorithm doesn't exist as far as I know for string reverse, so we don't really get to do that easily. All right, back here. So constant time, we really see this as the holy grail. And many times in an interview setting, there might be some way to execute some problem or to solve some problem in a kind of easy way, or there might be some very easy solution that might take, say, linear time or quadratic time. But your interviewer will say, oh, I specifically want you to solve this problem in constant time. So there's several problems that kind of fit into that category, and your interviewer might ask you to target a solution that meets one of these specific times. The next one is logarithmic time. So log right here stands for logarithm. It's like the math term taking the logarithm of a number. We will have a runtime of logarithm or logarithmic time if we double the number of elements that we are working with, or if we just increase them, but that doesn't exactly double the amount of work that we have to do. Logarithmic runtimes are most important whenever we start looking at any type of search algorithm. So searching through a sorted array of data, we can always assume that that might take an algorithm that runs with logarithmic time. And that's an important assumption, especially as we start to try to calculate the runtime of different algorithms. That's another note that we'll talk about in just a little bit as well. Linear time is one of the more common runtimes that you're going to see in a lot of interview questions, especially the more simple or straightforward ones. With linear runtime, you can easily identify this by seeing if you are iterating through some collection of data. So for example, in this course so far, every problem that we have had where we had to iterate through some string in some fashion, every single one of those has all been linear runtime. So in each of those, we had to iterate from 0 to some length of some collection, like an array length or a string length or whatever it was. And in each of those, we were probably working with linear runtime. Again, just like we were talking about with the reverse string function in the last video, anytime you have linear time, you are saying that if we add one element to our input set, it's going to take 1 unit of performance, or whatever you want to call it, 1 unit of more time to complete the algorithm. Now the next one, I had to look up the term, the technical vocabulary term for this one. I don't really like that name right there. Quasi-linear time, whatever you want to call that. Basically, n times log n. So this would be a runtime complexity that we would see if we start to increase our input set to our algorithm, but increasing that input set by 1 increase the amount of time it took to execute the algorithm by 1 plus a little bit. So 1 plus a little bit for every element we add to our input set. A very good example of this would be any type of, or I shouldn't say any type, but many different sorting algorithms that we might work with are usually going to be working with n times log n runtime. The next one is quadratic time here. So we just saw an example of quadratic time with our steps algorithm here. We had said that as soon as we started to increase or add one element to our input to the algorithm, it started to take dramatically more time to produce the result set. A very easy way of identifying an algorithm that uses quadratic runtime is what I like to refer to as the handshake problem. So an easy way to picture this, imagine a group of people standing in a room. If you send some additional person into that room and you introduced that new person to everyone else and you had them like shake hands, that would be essentially an n squared complexity. So each additional element that we add to a given collection has to touch or somehow iterate over or somehow deal with every other element in the collection. So you can kind of remember that handshake problem as an example of quadratic complexity. As another person was added into the room, they then had to shake hands with every other person. And every person in the room had to shake hands with everyone else. Finally, exponential time. So this is absolute, I shouldn't say this is worst case, this is not quite worst case, but it's one of the worst cases that we're going to be considering. So if we start to add a single element to a collection, the processing power significantly starts to increase. And so this is any type of algorithm that starts to use exponential time is one that we absolutely positively want to avoid. And we will see an example of exponential time in just a moment with one of the problems that we're going to work on. If you start to suggest an exponential time solution to a problem in an interview, that is a very big deal. That's a very bad deal, to clarify. Very bad thing. If we are able to identify an algorithm as requiring exponential time, we never want to propose it as a real solution to a problem in an interview. You definitely can, use it as a solution to get started, but very likely if your interviewer is proposing a problem or asking you a problem and you're thinking, oh, this will probably take exponential time to solve, chances are there's going to be a much better way of solving it. I can just about guarantee you. And that's what a lot of interview questions all revolve around. Your interviewer will ask you a question that might require exponential time or quadratic time, and so it's relatively a not very efficient algorithm. And you might be able to identify a solution very easily that uses one of these. And your interviewer is going to expect you to say, oh, well, I can think of a solution that uses this, but I can also think of this much more challenging and difficult to implement solution that might take linear time. That's what they're really asking in those situations. They want to see that you can recognize an algorithm as being inefficient and come up with some more efficient algorithm out of it. Okay, so this has been a quick review of some of the very common runtimes that we will see in action. Let's now take a quick break. We're going to continue in the next section and talk a little bit more about some common tips that I have for you about identifying runtime complexity. So quick break, and we'll continue with this in the next video.